Hello everyone, I am Pragya Srivastava. I am here to record a lecture on VLSI technology. The course code is KEC053 and previously I have started Unit 5 and presently we are discussing metallization. In my next lecture, I will start packaging of VLSI devices. In my last lecture, we were studying metallization materials. So we have studied that why aluminium is the most common material in the starting of this evolution, because the aluminium was having a property using which it can be deposited very easily. So since it has a low melting point, we can very easily make deposition of aluminium. Also, it has a very good property of good adhesion with silicon dioxide. So it is also an add-on, low contact resistance, easy to pattern since thermal evaporation, and can be integrated with resist lithography process. So next is aluminium silicon alloy. So when it comes to melting point, we have previously discussed that it has low melting point. So somehow it is a advantage. At one point of time, it can be also a disadvantage. So what happens if it has a low melting point? So when the integration density increases, when the components are more closely spaced, so even for a smaller rise in temperature, aluminium can start heating up and it can damage the entire device. So since because of low melting point, we have started going for alloy options. Aluminium in contact with pure silicon is heated. It forms an alloy with an eutectic point of 577 degrees Celsius. So this is a eutectic process in which the temperature is 577 degrees Celsius. This leads to dissolution of metal, especially in the form of shallow junctions, and lead to shortening of contacts as shown in figure 5. We have seen here what is happening is contacts with aluminium silicon contacts. What happens when this aluminium and silicon comes in contact with? When we are seeing that excess alloy leads to melting of aluminium, and here we are seeing that there is some excessive alloy and melting of silicon is taking place, melting of aluminium is taking place, and we can see that it is melted into a wafer and it has perforated and it has entered the wafer space. Next is silicide formation of metal layer by using aluminium silicon alloy. So here aluminium with silicon, we are when there is a silicide formation in the metal layer, that can be seen in diagram second. Next is barrier layer, that is the third thing. Barrier layer is usually deposited to prevent reaction between aluminium and silicon. So just as the aluminium and silicon should not react, here we have a barrier layer, and this barrier layer prevents this aluminium and the silicon to come in contact. So we can see that this was adapted by microchip fabrication, which was a joint venture of which was like a project initiated by Peter Van Zandt, and we can see that two solutions to this is, first is barrier metal, and another option is to use aluminium, which is aluminium with 1 to 2% silicon as contact metal. So this minimizes aluminium alloy with silicon, but it does not eliminate it completely. So thermal evaporation of aluminium silicon might now work due to large difference in melting points. So we can say that to reduce or to overcome from this problem, we can either go for silicides or we can use barrier layers. Next is aluminium copper alloys. So with increase in device integration, the thickness of the metal layer also decreases. Now, like we cannot have the tall and the tower like picture, so we have to reduce the thickness. So this leads to a problem of electromigration, especially in case of aluminium layers. So the electrons and the charge ions will migrate from one point to another, one material to another. So this is because thin film of the electric field gradient due to the applied voltage also develop a thermal gradient due to resistive heating. So this thermal gradient is very acute for thinner layers, and this causes heating and migration of material from thinner areas of wire, and as a result what is happening is they can cause an open circuit scenario. So due to this open circuit scenario, we have to think for a solution to reduce this electromigration, and this electromigration can be 4 to 5%, 0.5 to 4% reduced, and it happens when copper is added to aluminum. Copper alloys with aluminum, which is nothing but CuAl2, precipitates, and these precipitates pin the grain boundaries and reduce electromigration. They will just pin the grain boundaries, means they will make a stop points, and they will make a pin like stop bonds where the boundary is created using these pins, and there is no further electromigration. So sometimes silicon is also added to prevent this silicon dissolution from wafer. The typical alloy composition for a metal layer is aluminum would be 1.5%, silicon is 4%, and 4% of copper. So rest is copper. So next is what happens when we take pure copper. With smaller metal layers, aluminum and copper has high resistance, and we can see that pure copper contacts were introduced for the first time in 1980 by IBM. So it can be deposited with the help of thermal evaporation, and more importantly, it can be electroplated on the wafer. So hence a barrier layer, usually TiW, TiN, TaN and metal silicides is needed in this case. So these can be deposited by sputtering. So we have three methods: electroplating, sputtering, and other than electroplating and sputtering, we have chemical vapor deposition, physical vapor deposition. So as mentioned earlier, copper separates the wafer manufacturing from front end to back end. So this is another metal like pure copper. Next we are going to study what is the three mechanism: physical vapor deposition, electroplating and sputtering. So in this physical vapor deposition, we can see the diagram. We have to directly consider what happens in this. There is a thermal evaporator unit. In this we can see metal is vaporized by resistive heating and then deposited by wafers. So what is actually happening is, here is the evaporation source. So this evaporation source is just responsible for initiation or formation of vapors. Evaporation source is a tungsten filament that can be heated by passing current. So we are just actually making a circuit and passing a current. Multiple sources are possible in a single chamber, and at the top we have the wafer, and here we have the heaters as well, and this is nothing but the metal vapors. We can see here there will be metal vapors, and these metal vapors will come and deposit on the top of the wafers. So high vacuum condition like specific 5 into 10 raised to the power minus 5 torr to 1 into 10 raised to the power minus 7 torr, and of course we have a bell jar which is nothing but made up of quartz, and it is stainless steel. So there are a variety of physical vapor deposition technique, and just as a example, we have seen the figure just in the previous slide. The atoms and molecules like the vapor basically of the desired materials are directly deposited onto the substrate or the wafer. There is a different physical vapor deposition technique which differ on how the vapor is obtained. So physical vapor deposition is a line of sight deposition technique, so that the substrate must be in the front. So in the front of the source. The deposition rate depends on distance between the two, and the simplest physical vapor technique is thermal evaporation. and the scheme is shown in figure, and the material for evaporation is heated. So this was all about physical vapor deposition. Here also we have an electron beam unit. In this we can see that there is a crucible, and that crucible is water cooled, and we have just added a metal here, and using which we are just initiating a electron beam, and this electron beam is helping this is hitting into this metal, and from there we have this metal layers, metal vapors, and on the top of the setup we will be having certain wafers. So of course this metal vapors will go and deposit on the surface of wafer. This is another schematic. Here we can see that it is a process of sputtering deposition process. What is actually happening? There is what we call the metal here. Energetic high energy ions are impinged on the target. So these argon ions, they will just hit it. They will just hit, and of course they will knock out. This particular atom will knock out, and it will get deposited and settled on the surface of wafer. So it is deposited on the substrate. High deposition rate and decomposition control can be achieved in the process of sputtering. Another, we can see, this is a magnetron sputtering process. In this magnetron sputtering process, we have magnetic field at the top, and with the help of this magnetic field, we can see the schematic of magnetron sputtering process. Magnetic field are used to direct the electron beam to ionize the gas in front of the target. Now what is happening? We have this plasma, or we can see we have this target. Now this target is initiating the metal vapors, and this metal vapors, how these metal vapors are initiated? They are initiated with the high energy magnetic beams, and this increases the deposition rate, and greater contamination control is achieved in this process where magnetron sputtering process is being carried out. Next is chemical vapor deposition. We can see that chemical vapor deposition has been previously seen in the context of deposition, not in metallization, but we have studied it in deposition. So it is also used, and the method is almost the same. So CVD process is used for deposition of barrier layers, and this is good for large aspect ratio structures. In this CVD process, for growing conformal layers, deep trenches, we can see that we have to achieve this trench. This trench is achieved, and this is done when we are going for chemical vapor deposition. With the help of electroplating also, in this diagram we can see that there is a chamber. In this chamber we have CuSO4, that is copper sulfate. Schematic of electroplating process. Electroplating is usually for copper deposition. The seed layer is first deposited on the physical vapor deposition process using sputtering. Then the metal is dipped in the bathe containing copper ions. During electrochemical reaction, copper is deposited on the seed layer. We can see that there will be generation of copper ions and sulfate ions. So in the liquid we will be seeing that copper will be deposited on this cathode, and there will be anode on which this oxygen O2 molecule is seen to be approaching. So electroplating process is the most commonly used method for deposition of copper. The advantage of low cost, high temperature requirement it meets, and electroplating requires a uniform seed layer, and it is obtained by sputtering, and that seed layer is generally 30 to 200 nanometer thick, and this is reduced in the bathe, and the process leads to a copper overfill, creating a rough surface, and the excess material is then removed by polishing. So next is planarization, in which we can see planarization is a process of achieving a flat profile of the wafer surface. This is important for lithography. Since a flat wafer is needed to avoid registration errors, we can see when the mask is aligned after the wafer and to get proper focusing. So most deposition process produce a surface with infinite, which usually with finite roughness, which usually increases with increase in deposition rates. So we can see one is the non-planarized IC and another is the planarized IC. So non-planarized and planarized, we can see how symmetry is, how considerable change can be seen in symmetry. Non-planarized versus planarized IC, the difference lies in the roughness of various interfaces. See, here the interface is this rough, and here the interface is very much smooth. We can see it's very much smooth. So this is which leads to change in electrical properties. So this was all about metallization. In my next slide, we will start about packaging of devices, VLSI devices. Thank you.